Alright, we're looking at Unit 6 Energy for the remediation packet for physics. This is the guided practice. First, we're talking about work. Work, as we know, is defined simply as applying a force over a given distance in the same direction. Sometimes we will also refer to work, according to the work energy theorem, as a change in energy, which means work is measured in joules. So for part A here, we're looking at a graph that has force here on the y-axis and displacement here on the x-axis. So if we're trying to find the work, we need to do force times distance. So if we look at this as a rectangle, it looks like we're going out to 20 meters. So if we're looking at this point right here, at this point, which is 2100, that is where the force is equal to 100 newtons and the displacement is equal to 20 meters. So if I'm using my equation, work equals force times distance, it's as simple as plugging in these values. So my work is equal to 100 newtons times 20 meters, which will be 2,000 newton meters, also known as 2,000 joules. Work is equal to force times distance. In the second question here, it tells you that a student pushes a box with a force of 10 newtons for 15 meters. So we're still using the same equation. What you need to do is identify the components of it. What is the 10 newtons a measurement of, and what is the 15 meters a measurement of? Pull out your equation and make sure that you plug in the numbers into the right area. So you should end up putting those numbers in and performing the necessary calculation to get your answer. Make sure that you're showing all your work here when you complete these problems. So for part B, if you show your work correctly and work out the problem, you should end up with 150 joules. It's important that you get all the work shown. For part C, you need to show your work. There's also brings in the last equation that goes in with work, which is the rate at which work is done. Power is work over time. If you show your work for this problem, you should get an answer of 7,200 joules. Be careful that you follow your units correctly here. Here in the next part, we're talking about kinetic energy. So we have our kinetic energy formula, which you might write as E sub k, or you might write it as Ke, just depends on your preferred notation. But either way, this formula is equal to 1/2 mv squared. That tells us that mass and velocity are the keys here. But we also know that work is a change in energy. So if work is done to change the kinetic energy, then we might be using our force times distance equation as well. So we have some combinations that we need to make here. So in part A, it says a box is accelerated with a force of 50 newtons over 10 meters. Well, if you keep pushing a box for 10 meters and you apply a constant force of 50 newtons the entire time, that box is going to be moving. So in this case, the kind of energy that we're adding to the box is kinetic energy, and we're doing work to increase that kinetic energy. So work is a change in energy, and in this specific example, that change is kinetic. So force times distance will tell me what my change in kinetic energy is. And if we assume that the box started at rest, it started with 0 joules of energy, so all we have to do is figure out how much energy we gave it when we did the work, and we'll know how much energy it has. The problem gave us two numbers, 50 newtons, which we should recognize newtons is a measurement of force, and 10 meters, which we should recognize that meters is a measurement of distance. So if we take these and plug them in to where the equation is asking for them, 50 newtons multiplied by 10 meters will tell me the change in my kinetic energy, which will be 500 joules of kinetic energy. If we look at B, we have another example. This is a 1,200 kilogram car moving at 10 meters per second. So some hints for this problem, how you're going to work it. In this case, we know different pieces of information. So we don't know how much work was done on the car to make this happen, but we do know how much mass the car has and how much velocity it has. So we're going to be using this equation up here. And so all we need to do is identify which measurement is which and plug them into the proper parts of the equation and put them into our calculator to finish out that problem. And you'll end up with a large number in this case. Since we're talking about a car, we'll be talking about 60,000 joules. Remember, make sure to show your work to get credit for this problem. And for the last part here, if you work this out, a 10 kilogram object moving according to the graph, and we're giving position versus time graph, we're going to have to do a couple steps here, but if you show all your work and you come up with an answer of 20 joules, you should feel confident. In the next part, we're talking about gravitational potential energy. We're talking about potential energy, we're talking about stored energy, which has the potential or the possibility to do some work. In this case, the type of potential we're talking about is the potential due to gravity. So, the name gravitational potential energy can be represented by the variable, sometimes you'll see it GPE, sometimes you'll see it E with a subscript, maybe a G or a P or maybe both. Sometimes you'll see people just write PE and not be really specific about which potential energy they're talking about, because there are lots of different kinds. But if you infer from the problem, if they're talking about things falling, they're probably talking about gravity. So that is measured in joules, like all types of energy. We also need to know the mass of the object. That will be part of its potential energy. More massive objects have more potential energy. The acceleration due to gravity, the vast majority of the problems we're going to do will be as if they're done on the surface of Earth, which will make them very predictable. So not only are they in the units meters per second squared, but this is usually going to be 9.8, unless the problem specifically specifies we're on another planet or off of Earth. Lastly, we have height, which is really a special kind of distance. It is distance, but it's only distance in the vertical direction. Why? Gravity doesn't affect us horizontally, so we use h here. And we can measure this with a meter stick. So sometimes you'll see the equation for this written, gravitational potential energy is mass times gravity times height. But sometimes you'll see it written differently because of the fact that work is a change in energy. Then we'll see that work done to change the gravitational potential energy is a mass times the acceleration. And so MA, I'm really talking about force, and then the height is a distance. And so there's the age-old physics joke, work makes you mad, which is really just force times distance, the same equation. The second part asks us to find the mass of the object from the graph, assuming it is on Earth. They tell us it's assuming on Earth part, that way we know that the gravity is 9.8 meters per second squared. Then if we're looking at the graph, we know that the y-axis here is labeled as energy, and the x-axis is labeled as mass. So we need to be thinking about is what is the slope of this line. So we need to think about that in terms of our equation. So if the gravitational potential energy is mgh and the slope of this line is delta y over delta x, then what does that slope mean? And what does it mean in terms of that equation? If we rearrange our equation to have y over x. So make sure you see that the slope of the line is actually going to be two variables in there, so don't forget about your gravity. But if you show all your work and you end up with a mass calculated of 1.02 kilograms, then you got the right answer. And for part C, if you do your calculation of the gravitational potential energy of this 2.5 kilogram object that's 5 meters above Earth, if you use the equation, you come out to 122.5 joules of energy, then you've done it correctly. In this section, we're talking about elastic potential energy. Once again, this type of energy is potential because it has the potential to do work, and we're still using the work energy theorem, so work could be a change in energy, and that work could be a change in elastic energy if it's done something like to stretch a rubber band or compress a spring or something of that nature. My elastic potential energy is equal to 1/2 K, where K is that spring constant. We refer to it as the springiness or the stiffness of the spring, and multiplied by the displacement squared. Displacement is how far the thing has been stretched from its equilibrium position. It is not how long the object is in total, it's how far it is from its equilibrium at rest position. So that's our equation. This problem here says the following graph is a distance in meters versus force in newtons graph. It's a little backwards there. So the distance in meters it says is x, and the force in newtons it says is y. And it says determine the elastic energy after stretching 5 meters. So I'm also going to have to use my equation that force is equal to kx. Usually it's negative kx in this case, so we're going backwards. So that means if I'm looking for k in this case, because I really need this k to be able to finish out this problem. So k is equal to the force divided by that distance. So K is equal to 7.5 newtons divided by 5 meters, which I'm getting from this point right here. So that means my value for K is 1.5 newtons per meter, which I can then go and finish in this equation. So it equals 1/2 times 1.5 newtons per meter for my K times 5 meters squared here for my X, which if I put into my calculator, I will find that that equals 18.75 joules of energy. Looks like part B wants you to calculate the spring constant, K, which I guess I got a little ahead of myself and gave you. They must have won in the previous problem for you to calculate the area under the curve by doing that triangle 1/2 base times height. So make sure you show me the work for that. In C, what happens to the spring constant if the spring is cut in half? So remember what your spring constant is and how it relates back to the spring, and write out a good sentence there for how that should work. Now let's talk about the law of conservation of energy. This is where the real fun comes in. So we have the big idea of the law of conservation of energy. And it basically tells me that my initial energy and my final energy will remain the same, which is another way of saying that the change in total energy will always be 0. Which means if I know what form my initial energy is and what form my final energy is, I can set those two kinds of energy constant to each other. So part A says, a student throws a rock upward at 15 meters per second. What is the maximum height of the rock? So this requires some interpretation. First of all, I see a student throws a rock upward at 15 meters per second. We are talking about that initial energy there. That is a kind of kinetic energy. Because we're talking about it being thrown, we're talking about its velocity. And then it asks what's this maximum height of the rock. So we're saying that's at the end, the final energy. That's going to be gravitational potential energy. Well, if I know that the equation for kinetic energy is 1/2 mv squared, And if I know that the equation for gravitational potential energy is mgh, then I can simply plug these in. So 1/2 mv squared, which is the initial kinetic energy, equals mgh, which is the final gravitational potential energy. In this case, we're trying to solve for height, so we need to use a little bit of algebra here. Some of you might immediately be concerned about the lack of our knowledge of mass, but we'll see whenever we divide both sides by m and g, in order to get rid of the m and g that's being multiplied by the h, we're doing the opposite, so we divide, that not only will this m cancel here, but that m will also cancel there. So that whenever we end up rewriting this, we will end up with 1/2 v squared divided by g is equal to h. No mass needed at all. So whenever I plug in those values, 1/2 times the velocity squared divided by g, that equals my height. And you get an answer of 11.48 meters is your height. So you can see these final problems here are much more involved. The key idea is the law of conservation of energy, is that your initial kind of energy equals your final kind of energy, which means you're pulling out two equations and setting one energy equal to the other. So in this problem, it's another potential energy we have here because of the height. We see we have some gravitational potential energy from the height. We have some elastic potential energy from the spring. So we need to remember that our initial energy is going to equal our final energy. We need to look up the equations for gravitational potential energy and the equations for elastic potential energy, set them equal to each other. Then we need to solve for x. How far will the spring compress? And if you get an answer of 0.84 meters, then you should feel good about the work that you have shown. Remember that you're showing all your work here to get credit. Our final problem of this set, we have a paintball gun firing here, and it compresses a spring. If you do all your math here to find the spring constant, you should get a large number, 450,000 newtons per meter. If you get that and you feel confident about manipulating these equations, about interpreting these problems, about following the law of conservation of energy and tracking your joules around, then you should feel good about this guided practice and move on to the interactive practice.